Hi everyone, I'm Pengyu. Today I'm going to present a joint work with Marinela, Zhiqiang, Sarfraz, Alex, and Milos, unifying execution of imperative generators and declarative specifications. Before I get into the technical details, let me first tell you what's our motivations. Imperative languages like Java are the predominant way for implementing programs. Here I'm showing a Java code snippet for adding a value into a binary search tree. You don't need to look into the details of this code. Any implementation could contain bugs, or in other words, it may not match with the expected behavior. To detect and fix the bugs, developers sometimes write contracts in declarative specification languages to specify what a program is expected to do. Here is an example contract for the same program. Again, you don't need to understand the details, but I just want to show that the two programming styles are very different. Developers have mostly used contracts for checking the correctness when executing the imperative implementations. But recently, researchers are trying to execute the contracts directly using a set solver without imperative implementations. It can be useful in tasks like prototyping before writing imperative implementation, mocking a program when the implementation is not available, and solving some NP-hard problems where using a set solver can be even faster. However, using executable contracts has some limitations. First, the contracts need to be written in a declarative specification language, which can be quite different from general purpose languages that most developers are used to. Second, they cannot benefit from or be mixed with partial imperative implementation. So basically, an entire method is either executed declaratively as a contract or imperatively as a regular method. And third, the contracts are executed by translating to set formulas, which can be time-consuming and not scalable. In this work, we try to address these limitations by exploring the possibility of fusing imperative and declarative styles for writing contracts. So specifically, we enable writing contracts using general-purpose languages. We enable fused execution of imperative code and declarative specifications for a method. And we also enable executing contracts using in-memory states exploration. We name our contributions after the element used for nuclear fusion. Our framework, Deuterium, is for executing contracts as a combination of imperative generators and declarative specifications. So imperative generators offers a flexible and safe way to offload work from the solver. The Deuterium supports two constraint solving engines, a set-based solver, and for the first time in the study of executable contracts, an in-memory search-based solver. Deuterium comes with a language 2H, which is a type-safe domain-specific language for writing declarative specifications fully embedded in plain Java. To evaluate our framework, we post novel benchmark created using random and sequence-based test generation to mimic realistic execution scenarios. And we found that in-memory search-based solver can be faster, and using imperative generators do speed up execution of contracts. I will get into them one by one, starting from the framework. To use Deuterium, users write their contract as a combination of a generator in plain Java and declarative specifications in 2H, which is also embedded in plain Java. So users can simply use the default Java compiler, javac, to compile their contract written in a Java file. The compiled contract is executed as the following steps. Suppose the initial heap state at the beginning of the method looks like this. So we are to add the value 2 into a binary search tree with 5 nodes already. The first step is to check the preconditions. If the preconditions fail, then no need to proceed. Otherwise, in the next step, Deuterium invokes the generator, which should generate a backbone structure of the solution. In this case, it's an empty binary tree with 6 nodes. After that, Deuterium invokes the solver to execute the remaining part of the contract and fills in the missing values in the tree. I will explain step 2 and 3 in more details. The imperative generator should generate the backbone structure of the solution, for example, the shape of the binary tree, to offload some work from the solver. The code snippet at the right bottom is the generator we used for binary search tree. So basically, it generates a balanced binary tree without caring about the values of the nodes. Deuterium is flexible in terms of how to use generators. Basically, users decide whether or not to use the generator and what goes into the generator. That can be very different from case to case. And using generators is also safe. So basically, if the generators contain a bug, Deuterium can detect it because the post conditions and invariants are always checked at the end of the method. Deuterium supports two constraint solving engines, a set-based solver and an in-memory search-based solver. I will use this binary search tree example to illustrate them. So in the set-based solver, the first step is to translate the heap and specifications into relational formulas. So basically, objects are translated to unary relations. The mappings from objects to their fields are translated to binary relations. And basically, the relation we want to query here is the node value, basically the mapping from nodes to the values. The post conditions and invariants are also translated to some formulas using those relations. And then we solve these formulas using a relational logic solver called, which communicates with a set solver to do its job. It produces a relational model which contains the solution of the node value relation. And that is used to update the heap. And Deuterium implements this set-based solver based on a prior technique, Squander, but we also use some optimizations. Using the set-based solver requires the translations back and forth between the heap and the set solver, which can be quite costly. In this work, we also try a new approach to execute the specifications, an in-memory search-based solver, without those back and forth translations. So basically, based on the specifications, we set the search boundary. For example, each node can have this value ranging from 0 to 5. And then we create a predicate, also known as repo_k method, to check if the heap state satisfies the contract. So basically, it checks all the invariants and post conditions. Then starting from the first state, we explore the search space, check repo_k on each state, and stop at a state that satisfies repo_k. And that's the execution result. The state exploration uses the algorithm that effectively explores the search space by monitoring the predicate's executions. The exact algorithm is described in a prior work, Karat, but I will illustrate here using one state. Suppose we start from this state, and this table lists all the fields assignments at this state. During the execution of repo_k, we monitor the access to these fields. The repo_k starts by checking the invariants for all the nodes starting from the root node n0, and then we get n1's value to compare it with n0's value. And we found that n1, which is the left child of n0, has a larger value than n0. So that violates the invariance of the binary search tree, and the repo_k fails. And when we are moving to the next state, we notice that we actually do not need to mutate any of the n2 to n5's values, because they are never accessed with the current combination of n0 and n1's values. We only need to move n1's value from 1 to 2, and that prunes a large portion of the search space. Next, I will talk a bit about the language for writing declarative specifications to Edge. This is the contract for adding a value to a binary search tree in Deuterium. We've already seen the yellow part, which is the generator that generates the backbone structure of the solution. And I will talk about these remaining parts in blue boxes, and they are declarative specifications into Edge. And they are in first-order relational logic with transitive closures. The same logic is supported in Alloy and GFSL, so if you know any of those, 2H should be familiar. But different from those languages, 2H is fully embedded in Java. So developers who are not familiar with formal methods can also easily learn and use them. It's also very convenient for integrating Deuterium into existing projects. And 2H is also type-safe by leveraging generics in Java. I can't go into the details of this code due to limited time in this talk, but you can find more details in our paper. Next, I will describe how we evaluate the framework. Different from prior work that measures the time of executing the contract once, we create our workloads that resemble realistic program traces by executing sequences of method calls. So to create our workloads, we selected 12 data structures as subjects from prior work on testing as well as Java class library. So for each data structure, we write contracts for 3 methods: add, remove, and find in 2 ways, like the fusion of generator plus 2H and the pure 2H. We generate the 2 kinds of workloads. In randomly generated workloads for each data structure, we use Randoop, which is a random test generation tool, to generate X tests, where X is 100, 200, 500, or 1000. And the inputs to Randoop is the 3 method with contracts, the constructor, and the toString method. This is one example random test generated by Randoop. In systematically generated workloads, for each data structure, we generate all possible method sequences that lead to unique heap state up to X method calls, where X ranges from 1 to 50. Since the number of generated sequences grows exponentially as X grows, we only use 2 methods with contracts. And this example shows part of the method sequences in the workload up to 2 method calls. This table shows the configurations we experimented. We mix and match the 2 contract styles with the 2 solvers in different optimization levels. Those optimizations are described in the paper. In this talk, I will focus on these 4 configurations. I will focus on 2 research questions, comparing the execution speed of in-memory search-based solver and the set-based solver, and comparing the execution speed of the 2 contract styles. This table shows the execution time in milliseconds on the randomly generated workloads averaging across 12 data structures. Comparing the first 2 configurations, the set-based solver with generator and the search-based solver with generator, we see that the search-based solver can be faster than set-based solver. Now comparing the other 2 configurations, the set-based solver without generator and the search-based solver without generator, both solvers now have more work to do without the help of generator. And we found that the search-based solver is still faster on the smallest workload, but it becomes slower on larger workloads. That shows that the set-based solver scales better when the search-based is large. Now comparing the with generator versus without generator, specifically the two configurations in red boxes for the set-based solver and the 2 configurations in the blue boxes for the search-based solver, we can find that using generator can substantially improve the performance for executing contracts for both solvers by reducing the search space. And this plot shows the execution times on systematically generated workloads. The x-axis is the sequence length and y-axis is the time. You can see that the red line with square markers, which is the set-based solver with generator, is consistently faster than the blue line with X markers, which is the set-based solver without generator. We set a timeout of 30 minutes, and within that timeout, using the generator scales for 5 to 20 method calls longer than not using the generator. So that concludes my talk. More content can be found in our paper, as well as our GitHub repository. Thank you for watching.